This video shows you how to enter a new project in the Fire program. Click the File menu. Click New to create a new project. Notice that the caption of the main window says Untitled, which means we have not yet saved the project. It's important to save the project right away, since if your computer crashes before you've saved your project, you will lose all of your data. But if you've already saved the project, your data will not be lost. Click the Save button in the toolbar. Enter Example for the project file name. Click the Save button. The first four tabs of the General Project Data window have text inputs that are not used in the calculations but are shown in some of the reports. We will first fill in these four tabs and then continue with the video. Now we have filled in the inputs on the first four tabs. The inside hose stream allowance input lets you enter a GPM flow that is not used for any calculations but will be shown in the reports. You can enter the actual hose stations and flow rates later when entering your pipes. We will have one hose station, so let's enter 50 GPM. The default pipe material input lets you specify which kind of pipe material you want as your default. You may of course change this selection for individual pipes. Let's select pipe number 4, Schedule 40 wet steel as our default. This input lets you set a default K-factor for sprinklers in the project. You may change this for individual sprinklers later if needed. Let's enter 5.65 for our default. The rest of these inputs here are optional because they are not used in the calculations and are merely shown on the reports. The hazard description input is also only used for reference in the reports. Let's set it to Ordinary 1. The minimum desired density is an optional input that you may not need to enter at all for a small project like ours, where the GPM per square foot will surely be more than enough without having to enter a minimum. Let's leave it at 0. The sprinkler system type input lets us specify whether it is a wet pipe or dry pipe system. Ours is a wet system. The area of sprinkler operation lets you specify the total area covered by the active sprinklers in the system. Our system covers 600 square feet of floor area. The maximum area per sprinkler input specifies the maximum area to be covered by any one sprinkler in the system. For our ordinary hazard system, let's use 130 square feet. The next few inputs are used only for reference in the reports. We have only an inside hose station in this project, so we can leave the exterior hose flow box unchecked. It's very important to enter the hydrant test data in the next three inputs. In the reports, this data will be compared to your system's actual demand flow and pressure to show you whether the hydrant's pressure and flow are sufficient. The test static pressure is the measured pressure at no flow conditions. Our hydrant tested at 85 psi of static pressure. The test residual pressure is the measured pressure in the pipe while flowing the test flow rate amount of water. Our hydrant test flow rate was 202 GPM and the static pressure measured 77 psi. Now let's take a look at a diagram of the sprinkler system we are about to enter. Click the Help menu, then click Contents. Enter the word Sample in the box under the Index tab. Double-click the found topic, Sample Project Image. A circle with a number inside indicates a node of the system. This is node 20. This point in the system needs to be a node because it is for a sprinkler. A line between two nodes is a pipe. This pipe is in between nodes 10 and 20. Between nodes 10 and 60, there is a single pipe with this one elbow fitting. As long as both pipes connecting to an elbow are the same size, there's no need to make the elbow itself into a node. Instead, both pipes can be entered as one pipe. You would only need to make a new node here if the two pipes were not the same size. Every intersection, or T, will need to be a node. This is true even if all three pipes are the same size. Remember that a node number is needed only for a sprinkler, an intersection of more than two pipes, or where a pipe size changes. Click the Enter Edit Pipe Data button in the toolbar to open the window that will let us enter our sprinkler system. Each group of two rows on this window represents a pipe. The top row and the bottom row represent the two nodes to which the pipe is connected. The two rows of labels at the top of each column correspond to those two rows of data needed for each pipe. Our first pipe will be this one in between nodes 10 and 20. It doesn't matter which one is the beginning and which one is the ending node. Enter 10 for the beginning node and 20 for the ending node. Our pipe material number will be the same as the default of 4 Schedule 40 wet steel. All of our pipes in this project will be of the same material, so we don't need to change this value for any of our pipes. If we wanted to use a different pipe material than number 4, we could just click a different material from this list. We don't need to enter a constant pressure loss device or a fire pump, so we can leave the loss input on the second row blank. The fire program can select a pipe size for you if you leave the diameter input at 0, but for most projects you will already know which sizes of pipes you want to use, so you can fill in the diameter here. Let's enter 2.5 for our nominal diameter. If you are new to fire sprinkler system design, you might want to refer to the NFPA pipe sizing schedules in order to know which pipe sizes to enter. But those sizes will often be larger than you really need for the system to work properly. The length of this pipe is 10 feet, so enter 10 into the length input in the second row underneath the diameter input. Nodes 10 and 20 are both sprinklers, so we can select DFLT from the list, and our default K-factor of 5.65 that we entered earlier will be used. Another way to use the default sprinkler K-factor is to simply type the letter D. All of our nodes in this project will be at an elevation of 20 feet with respect to the 0 elevation line, which is normally the inflow node. Enter 20 for both nodes. The pressure estimate inputs, top and bottom row, let you enter a guess at the residual pressure available at each node for those rare situations where that might be needed by the calculations. But normally it's fine to leave these at 0. Once calculations are performed, these inputs will all be filled in with the calculated pressures, which will serve to speed up any subsequent calculations you perform. You only need to enter the sprinkler area, only for sprinkler nodes, if it's different from the value you entered on the general project data window. We will be leaving all these at 0 in order to let the default value be used. The area group input lets you group sprinklers that are near each other together into a group that you can easily turn on or off later as needed by zeroing the K-factors. This feature can be useful if it is not obvious which part of your pipe network is the hydraulically most demanding. We don't really need these inputs for this small project, but let's fill in our area groups from the diagram anyway, just for illustration. Remember that these two sprinklers were in area A on the diagram. The non-sprinkler flow inputs are only for nodes where you have a fixed discharge rate for a hose stream or an in-rack sprinkler allowance. We can leave these at 0 here. There are no standard or non-standard fittings, elbows, T's, etc., used on this pipe, so we don't need to enter anything in these two inputs. The pipe type input is only needed if you're going to let fire size your pipes for you. All of your pipes with the same integer number code here will be assigned the same size. Since we are entering our own pipe sizes, we don't need to use this input in this project, but to illustrate this feature, let's make 1 the code for 2.5-inch pipes and 2 the code for 1.5-inch pipes. Our next pipe will be this one between nodes 10 and 60. We can see that node 10 is a sprinkler node, while node 60 is an intersection node. And there is one elbow fitting between the two nodes. We don't need to enter the T-fitting at node 60 for our node 10 to node 60 pipe, since we will enter it later for our node 60 to node 70 pipe, since that pipe is the one that is at an angle of 90 degrees to the other two. Our nodes for this pipe are 10 and 60. Our nominal pipe diameter is 2.5 inches and our length is 25 feet. Remember that node 10 is a sprinkler and node 60 is not, so we need 5.65 and 0 here. Remember that 20 feet is our elevation for each node in this simple one-story system. Node 60 is in area C. Now we can enter our elbow fitting by typing an E in the standard fitting input. The optional pipe type can again be 1 here. Our next pipe is between nodes 20 and 50. Node 50 connects to 2 other pipes and also to a fire hose station. There is also an elbow on this pipe. Now we can account for our fire hose station by entering 50 GPM of non-sprinkler flow for node number 50. Here's our next pipe. It goes from node 30 to node 40, both sprinkler nodes. Here's our next pipe between nodes 40 and 50. Since this pipe is 90 degrees from the other pipes, we can enter the T fitting at node 50 by typing a T into the standard fittings input. Next up is the pipe from node 50 to node 90. Neither of these T fittings need to be entered here since our pipe is not on the 90-degree part of either T. The next pipe is this one between nodes 60 and 70. Next up is this pipe from node 60 to node 90. Since this pipe has both a T, the 90-degree part at node 90, and an elbow, we can enter ET in the standard fitting input. Now let's enter the pipe between nodes 70 and 80. Our final pipe is the one from node 90 to node 100. Since node 100 is our point of demand/supply, we will need to mark it as the inflow node. First, click in the input box for node 100. Next, click the Mark Inflow Node button to make node 100 our inflow node. We can see that a little arrow icon has been added to the left of the row for node 100, showing us that it is now our inflow node for the system. With all our pipes entered, we can now perform calculations. Click the Calculation button in the toolbar. The demand option is normally all you have to use here for relatively small or simple systems. It will run the calculations so that the hydraulically most demanding sprinkler will meet the residual pressure requirement you enter here. The supply option can be used for situations where the demand option didn't result in calculations being done successfully. It will take the pressure you enter here for the inflow node and calculate the resulting flows and pressures throughout the system. You should normally select this option only if you have a system that is not being solved by the calculations while in demand mode. Running supply mode once on such a system will assign residual pressures to the nodal pressure estimate input for each node, which should make it so you can then switch back to demand mode and have calculations performed successfully. For our small example project, we should only need to run the calculations in demand mode, so select the demand option. NFPA 13 says that the residual pressure for the hydraulically most demanding sprinkler must be at least 7 psi, so let's enter 7 here. Imbalance is the calculated difference in pressure between nodes. For a small project like this one, a maximum nodal pressure imbalance of 0.01 psi should be easy for the calculations to achieve, so let's enter that value here. For larger, more complex projects, you may need to use a larger value. The oscillation damping factor is a parameter Fire uses to control the nodal pressure adjustments it makes in attempting to find a solution. For a small project like this one, a value of 4 should be fine for the initial damping factor, and a value of 1 should work for the minimum damping factor. If a solution were to not be found with those values, we could increase them and try again. Now click the Calculate button. The system will be calculated, and we will see results on the Solution tab. There were no error messages from the calculations, and we can see various results on the Solution tab. Now let's take a look at the reports on the Print Preview window. Click the Quick Preview Reports button in the toolbar. We can see that the minimum residual pressure of 7 psi we requested occurs at node 30, the hydraulically most demanding sprinkler. The fire sprinkler output summary report shows us various important results, such as the demand flow at our system inflow node. The hydraulic supply/demand graph report shows us two curves, actually straight lines. The blue line shows the supply data based on the hydrant test data we entered. The dark red line shows demand data based on the calculation results. This point on the demand line shows the calculated residual pressure of 20.44 psi at 141.08 GPM. We can see that at that same flow rate, the supply line is well above the demanded residual pressure of 20.44 psi. The difference between the calculated residual pressure and the available supply pressure at the same flow rate is shown here. This value shows us that our supply at the hydrant is more than enough to meet the demands of our sprinkler system. Thanks for watching.